はい、では、定刻になりましたので、第13回目の計算科学技術特論 A を始めていきたいと思います。本日は理化学研究所のジュン先生に講演いただきます。本日は講義自体は英語でやっていただいて、最後質問はいつもの日本語で受けていただけると思いますので、So, the title of his talk is Parallelization of Molecular Dynamics、分子動力学の並列化という内容になります。So, please start, Dr. Jung.
Thank you for the introduction. And today I'll talk about the parallelization of molecular dynamics. で、分子動力学の並列に関係して話します。So sometimes I speak in English, or sometimes if it's necessary, then I'll also try to speak in Japanese. So first of all, I'll briefly explain the MD. So in MD, for every particle, we evaluate energy and force. And from the force, we can update the momentum. And from momentum, we can update the coordinate. So this is the equation of motion. So might be you also studied this one from F equals ma. And from this information of a force, we can update the momentum and coordinate. First of all, you can update the momentum by making use of force and making use of time step. And using this momentum, we can update the coordinate. And if we obtain the trajectory of this coordinate or momentum, we can make this one to generate ensemble. And after generating ensemble, we can evaluate various kinds of properties. For example, free energy or some very large conformational changes and so on. But to do this, we need very long time MD trajectory because this ensemble should be sufficiently large. If not, we might have some kind of statistical average for a very limited region, and such results might not be reliable and actually not accurate enough. So to obtain very reliable result, this large or long time MD simulation trajectory is very important. So here I show one example of MD integration. There are several different kinds of MD integration, but Velocity-Barrett is one of the very well known and very famous integration. So just let's consider at time t. At this time, we have a coordinate at time t, and from the coordinate, we evaluate the force. And after evaluating force, we update the momentum. From the momentum at time t to t plus half delta t. So now we update the momentum. Then, based on this momentum, we update the coordinate from time t to time t plus delta t. And after that, we have a coordinate at time t plus delta t. Then we can evaluate force at t plus time delta t. And based on this force, we update momentum from t plus half delta t to the momentum at t plus delta t. And we repeated this procedure over and over again. And from this one, we update the momentum to at time t plus 3/2 delta t. And based on this one, we update the coordinate. And now we have a coordinate at t plus 2 delta t. Then we evaluate the force. And we update momentum and coordinate and evaluate the force again and so on. So in MD integration, we should repeat this procedure over and over again. So one of the key points is that at every t, we need to evaluate the force values. So in MD, this force values is one of the very important things. But previously I mentioned that in MD, long time simulation is very important. But in fact, in our real application, long time MD is very difficult. And one of the main reasons is that the one time step should be very small. In biological system, we just limit the one time step to 1 or 2 femtosecond. So one of the main reasons to introduce a very small time step is each atom has a very high frequency vibration. And if we assign much larger time step, then there are many problems, including resonance. And in many cases, the force values are not accurate enough, and we cannot guarantee that this MD is okay. So one time step is very small, but on the other hand, our interesting results, so biological meaningful events, occur on the very long time scale. In some cases, even longer than milliseconds. And in this sense, we need to accelerate energy or force evaluations for long time MD. So you can see just this one. Atom vibration has a time scale from femtosecond to picosecond. And for biological system, some side chain motion have a time scale from picosecond to nanosecond. And protein main chain motion occur at microsecond time scale. And in many cases, we are interested in the protein folding. But protein folding requires millisecond level. And much larger protein global motions, we need second level. So this femtosecond is 10 to minus 15th power. And just obtain this microsecond level, we need 10 to 9 step force calculation. In other words, billion steps force calculations are necessary. So to go beyond this one is still very challenging and very difficult to work in MD. So this is a history of biological MD simulations. So the first biological MD simulations is done in 1977. But at the time, the target system is very small, just one protein named PPTI. And in this case, the number of atoms is just 600. So at the time, there was no water molecule. And we only consider the time scale is also very small, just the picosecond level. So around that time, we couldn't understand very long time behavior like a folding or something like this. But starting from this one, the time scale and system target system size is increased dramatically. So nowadays, for the same protein, but in this case, it has all of the atoms, including water molecules, and consisting of about 20,000 atoms. Now we can perform millisecond level MD simulation. And so compared to the target system size, the target system size is also increased quite much. The initial one was just 600, but using NAMD software, at some point, we could increase the target system size up to 65 million atoms. And recently also, they have about 300 million atoms. Also, in our group, using Genesis MD software, we also we could also perform very large scale MD simulation. So using K computer, it could perform about 100 million atom system. And recently, using Intel KNL machine, we can perform the billion atom system case. So I think still now, this is the largest target system size. But in fact, for this, even though the target system size is very large, in fact, the simulation time is very small. And still, we need to extend the simulation time and size. And to do this, I think one of the best way is to make use of efficient parallelization. So before saying that parallelization, I'll talk about what is the main problem in force calculation or energy calculation. What is the main problem? What is the main source of the time consumption? So in biological system, the potential energy consists of bond, angle, this one, and dihedral angle. Dihedral angle is the angle between the plane formed by the first three particles and the last three particles. So these first three particles will make one plane, and the next three particles also will make a plane. And between two planes, we can evaluate the angle. And between such angle, we can evaluate this dihedral angle energy term, and also improper dihedral angle term. And these are, we name it bonded interaction. And in addition to this one, we have van der Waals interaction and electrostatic interaction. This van der Waals interaction has repulsive power, repulsive interaction with inverse of Chebyshev power, and attractive term, which is proportional to the 6th power of 1 over r distance, and electrostatic. And if we just see the computational cost, here just assume that n is the total number of particles. Then this bond angle dihedral in improper, it has a computational cost of order of n. And the computational cost is not so high. But in the case of this non-bonded interaction, like van der Waals or electrostatic, you need to consider all atom pair. Because of this, it has order of n square computational cost. And this one becomes the main bottleneck in MD. And in MD, in fact, we need to consider much more. So in many cases, we consider periodic boundary condition. So what it is? Assume that this is the original system, and assume that these are particles. So in many cases, we need to make an infinite copy of this one, and we should consider this system. So basically, each particle has an interaction to infinite distance. And so just consider one particle here. If you see this van der Waals interaction, the first one has a 12th power of 1 over r, and the second one, this one has 6th power of 1 over r. So these two things decay very rapidly by increasing the distance. So in this case, we can make some kind of threshold values such that if the particle pair distance is longer than this one, we do not calculate at all. So here, for this particle, we define these threshold values, and we evaluate the interaction only between the particle pairs between this one and particles in this circle. So in this way, we can greatly reduce the computational cost of this one. But this electrostatic interaction, we cannot introduce the same kind of threshold values because these things decay very rapidly by increasing the pairwise distance. But this one has, as you see here, has 1 over R, R분의 1. So in this case, if we introduce this kind of threshold values, the force or energy is not accurate at all, and there are many problems. So in the case of electrostatic interaction, we usually decompose the interaction into real and reciprocal space. And in the case of real space, the real space term can be evaluated in this way. Here by making use of complementary error function. So 多分これ知らない人がいるかもしれないけど、多分これインターネットで探してみると、これがどの形かはみんなわかるようになると思います。So if we evaluate the electrostatic interaction in this way, because this one also decay very rapidly, we can introduce the same kind of threshold values even for electrostatic interaction. So in all interaction, we can introduce the threshold values, and it can greatly reduce the computational cost. But there are still long-range interaction, and such long-range interaction we are making use of. We are dealing using reciprocal space interaction. In other words, it is also named K-space or inverse space or and so on. And also there's additional term, but because this is a constant, we can just neglect this one in MD. So finally, we can consider the force evaluation in MD from real space and reciprocal space. In real space, we evaluate the bond, angle, and dihedral. And this real space, van der Waals, and electrostatic. And reciprocal space interaction, we are considering only the electrostatic interaction. So the concept of parallelization is very simple. Just accelerate the overall speed by reducing the computational cost in each processor. So just assume that if we calculate all of the interaction using one CPU, if we consider 16 times larger number of CPUs, can we accelerate the speed by 16 times? Then, if it's possible, then we can make use of parallel computation. But in fact, in every parallel computation, each processor needs to do some kind of communication. And also, you need to avoid the overlap of the same calculation. So the key point in parallelization is small amount of computation in one process. And also, you need to consider small amount of communication. Then let's move to to the parallelization. I think in previous lectures, you also learned the parallelization, a basic of parallelization, including the shared memory and distributed memory parallelization. So here I'll say only very briefly. In the case of shared memory parallelization, every processor shares the same memory. So, for example, one processor can calculate something and they can save some memory. Then other processor later could use the data generated by different processor because they share the memory. And one of the main representative of this shared memory parallelization is OpenMP. If you use C, you can use Pragma OMP parallel. If you use Fortran, you can write OMP parallel. So good thing is, so I think many people are developing code using this OpenMP because it's easy for every source code. By making this kind of directive, you can easily parallelize the code and you can easily accelerate the overall speed. But in this case, according to my experience, one thing you should be very careful, need to be careful is that every processor should not access the same memory address. So for example, this process writes something here, but at the same time, this processor also writes something here. Then what will happen? Then there will be some problem in overall calculation. So when you write the program, you should be very careful in confirming that these different processors access different memory. So in the case of reading, it's okay. So this processor and this processor, they can read the same address. But assume that when writing some values on the same memory address, if they access the same address at the same time, what will happen? So this is the very critical consideration when you write the shared memory parallelization using OpenMP. And also, here I wrote that it is only available for multiprocessors in a physical load. So assume that you have a single load, and in a single load, you have one CPU. And in one CPU, you have, for example, 6 cores. Then you can apply this OpenMP parallelization. But if you have 2 nodes that are physically apart to each other, even though they are connected by network, you cannot apply this shared memory parallelization. So please keep in mind that this shared memory parallelization is available, only available for multiprocessors in a single node. The other parallelization scheme is distributed memory parallelization. And one of the representative is MPI. So I think you know the abbreviation of this MPI, message passing interface. So in this case, they are communicating by sending and receiving their message. So in this case, each processor has different memory. So if a processor 1 writes something on memory, the other processor cannot access this memory. So because the memory is not shared. So in this case, between processors, we need communication. And in this case, we need to send and receive data to each other. And for sending and receiving, we need some kind of key to match to each other. For example, this one wanna send the data to this one, this processor. But if this data went to different processor, then the result will not be accurate any longer, and we cannot proceed the calculation. So some kind of such a matching processor between sending and receiving is very important. And also, for efficient parallelization, the amount of this communication data should be as small as possible. So in the case of MPI, we usually start from MPI in it, and we just call the MPI com length. And from this one, each processor understands their length. And they also understand how many processors are there. So the next one is hybrid parallelization. So in almost cases, you are making use of hybrid parallelization. In this case, we combine distributed memory parallelization like MPI with shared memory parallelization like OpenMP. And first of all, we so each processor, we first distribute the processor according to MPI. And inside the MPI, each processors, they can share the memory together. And in this way, in some cases, parallelization with MPI is very difficult. And in some cases, parallelization of OpenMP is not so efficient. And by combining these two things, we can obtain the best parallel performance. And if you consider very small number of processors, then I think you don't need to consider this hybrid parallelization. But if you consider very large number of processors, then I think it will be better to consider this hybrid parallelization. So source code is like this. First, if we call the MPI related things, call MPI init, MPI com length, and so on. And it's in each part, we parallelize by making a directive of OpenMP directive. And also, another thing you should consider is the very low level parallelization, like SIMD. So single instruction and multiple data. So in a computer, sometimes you might hear that this is 64-bit machine. This is 128-bit machine, or 256-bit. So for example, in the case of Fugaku, it's 512-bit. But in many Intel machine, it's like 256 bit. だから富岳は512ビット。で、他のインテルは256ビット。そのようになると、これ何ビットによってスピードがもっと速くできます。これはSIMD、このSingle Instruction Multiple Data を使うからになります。Then let's consider what is SIMD. So let's consider some kind of calculation like the matrix, the sum of matrix A and B, and obtain the matrix C. So we can calculate in this way. First, the first element of A and the first element of B is added, and we obtain the first element of C. After finishing this one, we add the second element of A and second element of B, and we obtain the second element of C, and so on. But if we apply SIMD, then from the first to fourth element can be considered as one element. And from the first to fourth element of B is also considered as just one element. And we can just apply this addition just once to obtain the fourth element of C. So by making this way, we can accelerate the speed 4 times. And for example, if we consider Fugaku, it's I said that it's a 512-bit machine. In other words, it is 32-byte machine. But one floating point or integer, floating point is a single precision or integer. If we consider 4 byte, then 32 byte is 8 times larger than 8 times of 4 byte, which means that we can do this kind of thing. We can do just 8 addition. I'm sorry. 日本語で言うと、この足し算を8回やることが、足し算1回で深くでやったらできるようになります。で、この8つの8エレメントの、足し算のものが1つに考えて、これが足し算が1回の足し算になるんで、他の計算が簡単な計算だったら深くでやって8倍早くなる計算になります。So in many cases, so when you write the program, you should consider this kind of parallelization. I think this is some kind of a basic consideration when you, if you wanna accelerate the speed of your program. Then let's move the MPI parallelization of MD. In particular, let's consider non-boundary interaction in your space. So the first parallelization scheme you can consider is deprecated data approach. This is a very simple one. So in this case, each process has a copy of all particle data. And each process works, only part of the whole works by proper assignment into loops. So just let's see the example. Here we have a I index starting from 1 to n. And for each I, we make a iteration based on the j starting from I plus 1 to n. And here, for every ij pair, we evaluate energy and force. Just consider this kind of code, how we can parallelize the code. So this is one example. By using MPI, we define the MPI length. So each processor has a different number of this length. And this total MPI, just assume that is the here PROC. And if we change just this one to this way, then you can parallelize. So based on this length number. Some processor skip the unnecessary calculation, and we can reduce the total computational cost. But problem is that after doing this one, every processor has some kind of partial data. So after doing this, we need communication to get the final energy and force values. And in this way, so we cannot obtain the perfect load balance. So let's back here. Because this J is dependent on I, they start from I plus 1. So when I equals 1, the amount of J will be large. But as we increase this I indices, the amount of this one will be reduced. So in this way, the first length will have a very large computational cost. The second one will have slightly reduced the computational cost. And by increasing the length, the amount of work will be reduced by increasing the atom indices. So in this case, because of this situation, it will be very difficult to obtain the perfect load balance. So load balance means that every processor finish the calculation at the same time by doing same amount of calculation. But in this case, some processor, some length might have a more computational cost, and some other processor like this one will finish the calculation much faster, and they will just wait. And because every processor have all of the data, the communication also can be very large. And similarly, based on this scheme, we can also consider the hybrid parallelization in this way. This is just an example. I think there will be many ways. So let's consider one example here. So if we consider only the MPI parallelization, based on MPI length, we can parallelize in this way. This is same as the previous case. But if we have a hybrid parallelization, then we can make a new ID identifier by combining the length MPI length number and open MP set number. So like MPI length, in OpenMP parallelization, we can assign the OpenMP set identifier to each processor. And by combining them, we can just simply change the first line, the first loop in this way, and you can parallelize the whole code. Or also there's other way, like this way. The first loop, we are only parallelizing by OpenMP. And the second loop, we can make OpenMP parallelization. So in fact, there is no straightforward way to do parallelization. It really depends on the case and depends on the algorithm. So, but here I wanted to say that there are many ways to accelerate the speed or parallelize the code by combining the length ID of MPI and OpenMP, or just using length ID of MPI only. Then, what is a good thing and problem in this approach? The good thing is that you can easily write the code. It's easy to implement. But in this way, first of all, parallel efficiency is not good. Load balance is difficult. And communication cost is not reduced by increasing the number of processors. And in fact, this one needs a lot of memory because they need to have all of the data. So nowadays, some program may use of this parallelization scheme, but almost MD software for efficient parallelization, they do not make use of this kind of parallelization scheme. And almost the program make use of this parallelization scheme named domain decomposition. 日本語では区間分割のスキームで話します。So in this case, the whole simulation space is divided into subdomain like this one. And each subdomain space is assigned to MPI. So here I assumed 9 MPI, and in other words, 9 MPI processor. And each MPI or each processor calculates only this part, each part separately. So one processor, one MPI corresponding to this region. They do not care the data of this one. They only calculate energy of this region. And the next MPI only calculate the energy and force of this region. But in some cases, we also need to consider the interaction between particles here and here. So in this sense, we need MPI communication. But we don't need to care the interaction between here and here. So we consider communication only among neighboring processor. So this one, the processor only consider the communication between this one and this one, this one, this one, and this one only. And even the communication cost, they don't need to communicate all of the data. They can only communicate the data around this boundary region. So by making this way, we can greatly reduce the communication cost. And another good thing is that each processor, they have data only this region. So the memory usage is also reduced by making use of this scheme. So in this case, so please remember that I mentioned the threshold values in van der Waals and real space electrostatic calculation. Because of this, in fact, for each particle, you need to have the data of not only this region, but also some kind of buffer region. And this buffer region depends on the such threshold values. And if each processor has the data of this region, subdomain region, and additional buffer region, then they can somehow calculate energy and force. So to do this, so each processor need to have the data of the buffer region. And this buffer region depends on the such threshold values. And using this way, the interaction between particles in different subdomains should be considered very carefully. This one means that, for example, let's consider the particle here and here. So for the such interaction between these two particles, this MPI can calculate it. But if this MPI calculates the interaction, this one, must not calculate it. If not, for the same interaction, two calculations can be done, and it can make some problem. So in this sense, for the interaction of between particles in different subdomains, assignment is very important. And if you consider this one, if we increase the number of processors, then this subdomain size becomes small. And even though we consider this buffer, the overall subdomain region can be small. And we can reduce the computational cost in this way by increasing the number of processors. Then let's see what is good thing and what is bad thing of this domain decomposition. Yeah, good thing is that it has a good parallel efficiency. So by increasing the number of processors, we can reduce the computational cost. And we can also parallelize not only the energy force calculation, but also other part. And because of this way, in fact, this domain decomposition is very good for very large system. By increasing the number of processors, the memory usage is reduced, and we can calculate, it can evaluate MD even for very large system. In this case, there are many things to be considered. And so in this way, implementation will be more time consuming. And in many cases, this domain decomposition is highly dependent on the potential energy type, cutoff, and so on. So you should be very careful when we implement this domain decomposition parallelization. And another thing is that just making the same, so just assign the same amount of this subdomain, we cannot obtain the good performance for non-uniform particle distributions. So for such kind of non-uniform distributions, also many people consider different way, like tree method or Hilbert space filling curve. So and also there are other methods. If I say just the tree method here, just assume that this point is a particle. Then first of all, they make a division of this one, such that left and right have the same number of particles. And also for this way, from this one, we make in some part we assign the much larger subdomain. In some part we assign much smaller subdomain, such that each subdomain has the same number of particles. Also right side also like this. So based on this tree method, there are several variants, and you can consider many ways to do it. And another Hilbert space filling curve is that this three-dimensional map is mapped to one-dimensional curve. And by excess bushing according to this one-dimensional curve, we can make a domain such that you can make a subdomain such that each subdomain has the same number of particles. So anyway, so in fact, my point here is not this kind of tree method or Hilbert space filling curve. So please forget this one in this presentation, and please consider uniform particle distribution. So in this case, here I explained the two schemes, replicated data and domain decomposition. In both cases, we can reduce the computational cost by dividing the whole computational by dividing the number of processors. But in the case of communication, this domain decomposition can reduce it much more. And also, this domain decomposition has much small amount of memory. Then how about the reciprocal space calculation? So let's back to electrostatic interaction. You make by using a particle mesh unit scheme. In fact, in electrostatic calculation, there are many parallelization ways. And here, I only explain the most widely used scheme. And the most widely used scheme is mesh URD scheme. So as I show in previous slides, the electrostatic interaction can be decomposed into three interactions. One is real space. In this case, we introduce threshold values. And the other is reciprocal space interaction. And in this reciprocal space interaction, we change the charge data according to the grid values, and we are performing fast Fourier transformation. And the other is self-energy term, and I said that this is just a constant, and this one does not increase any computational cost, and you can just neglect it from the computational cost point of view. And point is that in this reciprocal space interaction, we need fast Fourier transformation. So in reciprocal space interaction, the parallelization in reciprocal space interaction, it is very important to how to parallelize the fast Fourier transformation. Also, in reciprocal space calculation, not only fast Fourier transformation, also there are several things to consider additionally. So we need some kind of charge on grid data. So to do this, we first convert the charge on real space to charge on grid data. This is the first step. And after that, we are performing FFT. And based on these FFT values, we evaluate energy. And there are also some prefactor. And such prefactor values and these values can be calculated or evaluated using convolution on real space. But on reciprocal space, we can just multiply them. And after multiplying them, we perform inverse FFT. And after performing inverse FFT, we can calculate the force values. And also, before saying the parallelization of this reciprocal space calculation, please remember this MPI all-to-all communication. So here, just consider two matrix with two dimension, and assume that the first processor has a data of A1, A2, A3, A4, and second processor has the data of from B1 to B4, and third processor has the data from C1 to C4, and so on. This MPI all-to-all command change the data in this way. So originally, process 1 has the data of A1 to A4, but after doing this one, this process 1 will have the data of A1, B1, C1, D1, A1, B1, C1, D1. And second processor will have the data of this one, A2, B2, C2, D2, and so on. So this MPI all to all is the same as matrix transport. And in reciprocal space electrostatic calculation, we are making use of this MPI all to all. The first parallelization of FFT is slab decomposition. In this case, we are only divide among one dimension with the P processor. So each processor will have the data of this slab-like one. So for FFT in this direction, they have each processor has a global data of FFT. So for this, they can just do FFT calculation. And after that, for FFT in this direction, yeah, each one has a also the global data in this direction. So for this one up to here, there's no communication necessary. But for performing FFT in this direction, each processor needs to have the data of global data in this direction. So in this case, we need MPI all-to-all communication among all processors. So in slab decomposition FFT, we perform only one MPI all-to-all. So good thing is that this one is fast if we use very small number of processors, but it has a limitation of the number of processors. And another FFT parallelization widely used in many MD software is 2D decomposition. So each processor has a data, local data like this, this pencil-like one. And first they perform FFT in this direction. And after that, to perform FFT in this direction, among these three processors, we need MPI all-to-all. And also this one, we need MPI all-to-all communication among three processors like this way. And after that, to perform FFT in this direction, each processor, three processors we need to perform MPI all-to-all. So in this case, we need two MPI all-to-all communications. So good thing is that, in fact, it requires, so we can make use of much larger number of processors than one-dimensional decomposition scheme. But if we use very small number of processors, then it can be slower. And the overall scheme is like this: FFT, communication, FFT, communication, and FFT. And also, there are three-dimensional decomposition scheme. In this case, each processor has a data of this qubit. And to perform FFT in this direction, these four processors have auto communication and have the data in this way. And you can perform FFT. And then this data is back to this style. And to perform FFT in this direction, this four processor, we need MPI all-to-all and have the data this way and do iterative one. So this one requires more communication than existing FFT schemes. But good thing is that the number of MPI processors involved in communication is small. So here, for this communication, we can consider only 4 processors and other 4 processors zone. So although here I assumed 64 processors, the number of processors involved in the communication is just 4. So it can be very useful when you perform very large scale calculation. And based on this, I'll talk about the parallelization of genesis on Fugaku supercomputer. So we have a Genesis MD software history like this one. And recently we opened Genesis 2.0. And I think you can download and you can use the MD software Genesis by going to this web page. Because this is a free software under LGPL license, you can easily execute, or you can also check the source code. So in Genesis, we are making use of domain decomposition. So the whole space is first divided by subdomain according to number of MPI. So here I assumed 9 MPIs. And each MPI we further divide into the unit domain here, named cell. So each subdomain here have 16 cells. And the size of each cell has the threshold values. And we are considering communication only between neighboring processors. And also between this and this processor, we are considering communication of only this one. We don't need to consider communication of other cells. We can consider communications only the adjacent cells of this boundary. And in each subdomain, we are applying open-MP parallelization. So because we are making your cell, so when you consider programming, one of the important things is how to make use of a memory very efficiently. So in our cases, we locate every particles according to cell-wise, and the particles in the close distance also are very close in the memory also by making use of cell-wise array. So arrays are defined according to cell, and the particles in the same cell are also very close in memory. And based on this one, we made use of a midpoint cell scheme. And this midpoint cell scheme, you can consider particle in different domains. For example, if you consider particle here and here. So in this case, the criteria is decided based on the midpoint cell. So you can consider the cell including this particle and the cell including this particle. And for these cell pairs, the midpoint cell is here. And we consider the interaction between particles here and here is considered here. And the MPI processor, including this cell, is this processor. So this processor calculates the interaction between the particle located here and here. So in this way, for every particle pair, we can efficiently evaluate the pairwise interactions. And so it's like this. So in this case, each particle has a data of here, and also from the neighboring, they need a communication. Then they can import the data of this yellow color, orange color region. So each processor has the data of this blue one. So in this case, this one. Example, this subdomain is this blue one, and some additional, this marginal one is this orange one. And they calculate all of the interactions. And so in our hybrid parallelization, we first make a sense of the whole for the whole system. And this whole system is first divided into many cells. And according to the number of MPIs, we assign the multiple number of cells to each subdomain. And each subdomain, for example, has the subdomain data of this one. And during communication, they have also data of this region. And from the communication from up and down, they also have the data of this region. And each processor has the whole, only you make use of this data, then they can calculate it by making a cell indices. So for every particle pair, we first sort them as a cell pair. And by making all cell pairs, for every cell pair, we checked if their midpoint cell is located inside of this subdomain or not. For example, this one, for example, 130. 130 is, even the midpoint is inside of this domain, so we assign yes. But in some cases, for example, 313, so it depends on, in some cases, we can, if the midpoint is assigned as 3 or inside of this domain, we check the yes. If not, we do not calculate it. And we only check the midpoint cell cases. Here, yes, 1. And this one is, again, parallelized by OpenMP. And this one is the hybrid parallelization in Genesis. And it basically makes use of this kind of parallelization, but for high speed on Fugaku, we selectively modify the scheme. So previously, every calculation is based on this cell pair. So assume that the first cell has the atom indices like this one. And second cell has the atom indices like this one. And within the threshold values, so here, circle is that they are very close to each other within threshold values. Then for every cell pair, we first make an atom index of first cell, like here, 1, 2, 3, 4, 5, 6, 7, 8. And then we check the atom indices in the second cell pair. So, for example, here, if Ix equals 1 here, then these Jx values become 1, 3, and 5. Here, if atom index is 2 in the first cell, then these Jx values become 2, 5, 6, 7. And we are making this kind of way. As for Fugaku, I think you can understand the information, so I'll skip here. Then, on Fugaku, we found that, based on the co-design, we found that there are several things to be considered. One thing we should consider is, for this one, to understand it, let's consider 2 algorithms. Here, we make an atom particle indices of I from 1 to 16, and another J indices from 1 to 16, and evaluate Fij. In other algorithm, this Ij, 2 loops are combined into 1 and making indices from 1 to 256. So basically, in principle, there should be no difference between these 2 algorithms. But we found that on Fugaku, this algorithm has a better performance. And we found that the 2 loop lengths in the most inner 2 loop should be as large as possible. So here, the inner 2 loop, the length is 16. But in this case, the length becomes 256. And by making use of SIMD more efficiently, we can obtain much better performance by increasing the length of this doodle. And also, we found that if the doodle is very small, then we also found that it's better not to apply SIMD. So based on this way, originally we make an atom indices in each cell. Sorry, cell status here. But finally, we thought that it's better not to use this of cell indices, but just atom indices in each subdomain in this way. So I can say it's a little bit complicated. So one thing I can say is that in previous cases, for each cell pair, we make a doodle of this one and this one separately. But for the same particle, for this one, we can make a doodle of one doodle together, and we can make large doodle length for each particle. So previously, the first particle of first cell has a doodle length 3 and 3, and here 6 and 3 separately. But on Fugaku, by combining them together, we make a much larger doodle length. Yeah. So I just do this way. And by making use of this way, in the original one developed for Fugaku, has a doodle length distribution like this one. But by changing the algorithm, we have a much larger doodle length. And in this way, we could increase the overall speed quite much. Also, on Fugaku, by making use of prepatch, we can also increase the speed somehow. And in the case of this reciprocal space interaction, and this is what so here, if I just focus on this part, so how to make charge on grid data. So basically, for charge particle in real space, it is distributed the charge values on this grid point. And to do this, in fact, to obtain, so in fact, to do this originally, each processor has a data of this subdomain and this buffer region. They can generate the charge grid data of this one. And among them, and we only pick up the charge grid data of this one, and we calculated it. But on Fugaku, we found that this way can avoid communication, but somehow requires more computational cost. So why we need this kind of unnecessary things? So in our cases, we are considering only the charge grid data of this subdomain only. And after this charge grid data of this subdomain, we will generate data of charge grid data like this way. And by making, and from this one, by making use of a communication, we send the data of this one to upper and lower processor and send this data to left and right processor. And by doing this kind of local communication, we can reduce the computational cost and we can increase the overall speed. I think I do not have so much time. So, but here, this is one thing I have one thing to say, which is not related to MD, but related to only Fugaku. So if you see this code, let's see this code. This has some kind of recurrence relationship. First, you have start 1 data. And because based on start 1 data, we have a start 2 data. And based on start 2, we obtain start 3 and start 4 and so on. But if we compile this one on Fugaku, then if you see the compile log result, you can see this one. Here, V means that it is vectorized. In other words, it is SIMD is applied. The problem is that if we apply the SIMD, then start value at I equals 2, 3, 4 is done at the same time. So, and it does not have the correct or accurate values. So, SIMD can be applied when there is no dependency over these I indices. But sometimes Fugaku compile with vectorization, even though there is such kind of relationship. So in this case, you should be very careful. If you just write the code in this way, if you compile on Fugaku, then the result will be wrong. And in some cases, you need to check if it is vectorized or not by checking the compile log. And if it is vectorized, then you need to check if there is no dependency or not. And in my case, on Genesis, one way I avoided using this pointer and just write it directly. Or on Fugaku, I used no SIMD directive. You can also consider these kind of things. And yeah, by making use of Genesis, by applying several optimization scheme on Fugaku, we could accelerate the speed from this one to this one. And also the pull-ups is increased from this one to this one. And also non-bounded list generation used in MD is the computational time is reduced from this one to this one. And by making use of a new PME scheme, we could use much small number of grid points, and we can reduce the fast Fourier transformation calculation. And finally, we could obtain very good result. So this one is a weak scaling result. And finally, it could even perform 1.62 billion system. I think this one is the largest system all over the world. And for this system, you can perform this way. And also for 1 billion system and 100 billion atom system, now by making use of several things, we could obtain much better performance than K. For example, for 100 million atom system, we obtain 4 times better performance than Genesis on K. Although we are making use of only the 1/8 number of nodes. So this is a summary. So parallelization, here I explained the MPI and OpenMP. MPI is one of the representatives of distributed memory parallelization. OpenMP is shared memory parallelization. But in many cases, we are making use of hybrid parallelization by combining MPI and OpenMP. And in MD, we are parallelizing many by domain decomposition. And please keep in mind that the key issue in parallelization is minimizing the communication costs and to reduce minimizing the computational cost also. And we also need to consider hardware-aware optimization. That's all. Thank you.
Thank you very much. ありがとうございました。